Hello everyone, welcome to Code Presents. I'm Philipp Bauer and today I'm going to show you how to implement and use large language models in your C# application. A little bit about me first though. I'm a senior software developer at Code Consulting and I have over 15 years of experience of developing software for companies in the medical, industrial and insurance industries. I'm also a trained media designer for digital and print media. I've been curious about different aspects of language models, like many, since ChatGPT hit the market. I think the open source LLM community is especially interesting if you're curious about current developments and how they work in general. My interest was piqued when I was trying to create characters for my Dungeons and Dragons games and ChatGPT wouldn't create any interesting characters anymore. So before we start, let me introduce you to the code group. The code group consists of 4 arms: consulting, staffing, the magazine, and training. Our mission is to help you build better software. We are experts in custom software development with a recent emphasis on artificial intelligence and copilot development. We specialize in legacy conversion projects and project rescues. And beyond that, we also offer application security testing and we provide support and maintenance for existing applications. We're really excited to introduce you to our new AI offerings, the executive briefing. If you're wondering how AI can help your business, or if you worry that privacy or regulatory issues might stop you from using AI, this is for you. The executive briefing provides guidance and concrete advice. We help decision makers move forward in this rapidly changing landscape. If you're interested, please visit codemag.com/executive briefing. At Code Staffing, we're disrupting the staffing world. We provide our customers with highly skilled and capable personnel for their specific needs. We're taking a bold step by offering our staff industry-leading benefits, creating a win-win situation for everyone. We are also actively hiring across all of Code Group. If you're interested in joining us, please visit codestaffing.com/careers. And we have our upcoming State of .NET event on November 15th. Marcus Egger will highlight the key takeaways from .NET 8's release. To register, go to codemag.com/stateof.net. And if you can't wait that long, get a free subscription to our Code magazine. We also have a special issue, the Code Focus. Each focus issue delves into specific topics like MAUI or the newest .NET releases. Follow the link here on the slide to claim your free subscription to Code magazine. And as with every Code Presents, we're conducting a survey with a chance to win a $100 Amazon gift card. To be eligible, the survey must be completed by Friday, October 27th. You can either follow the provided link here or scan the QR code to participate. We'll show this slide after the presentation again. Before we start, let's look at what we will learn in today's session. First, I will answer the question why you would want to run a language model locally. Then we will take a look at factors that decide which model is right for your use case. Then we will look at how to integrate large language models in your C# application with Llama Sharp. We'll take a look at an Instruct demo, at a chat demo, and we will compare different versions of the Wizard LM large language model. So let's dive into that. Why would you want to run a language model locally? There are many reasons why, but the following 3 are my 3 most important reasons. The first one is control. The second is privacy and compliance. And the third is offline access. What does it mean to be in control? Services that offer LLMs may change their model at any time. And this was demonstrated in a paper from around mid-2023 titled how is ChatGPT's behavior changing over time? You'll find a link to this and other papers in the description below. In this paper, the authors tested GPT 3.5 and GPT 4 on a range of questions and recorded the answers. They wrote that overall, their findings show that behavior of the same LLM service can change substantially in a relatively short amount of time, highlighting the need for continuous monitoring of LLMs. Some of these changes are due to the need to make models safe for everyone to use. But this is a tough issue to solve, and it's hard to get right for everyone. So you might find yourself with a use case where these safety mechanisms don't allow the language model to give you an answer. In this case, you might find a solution in a local language model. But as always, with great power comes great responsibility. And you will be responsible to ensure a level of safety, either through fine-tuning or other measures, if you use these in production. My second reason is privacy and compliance. Privacy can be an important issue for your organization or for your product. And this might keep you from sending data from your application to a third party like OpenAI. If you have to keep your data on premise, using a local language model might be your best option. Imagine, for example, that your data is bound by regulations like HIPAA, and your service provider can't offer this level of security and certification. This is just one scenario where a local language model can solve this issue. And last but not least, offline access. If you have an application that needs uninterrupted access to a language model, you can't count on a service to be available. Maybe you build an application that uses a language model to translate on the fly, and interrupted internet service will render a potentially critical app for your user inoperable. So, if your use case requires either control, privacy, or offline access, then a local language model might be the right choice for you. How do you choose the right model though? Selecting an appropriate language model for your specific needs involves several key distinctions that are worth understanding. These distinctions are model types, sizes, the training data that was used, quantization formats, file formats, and licenses. Let's take a look at model types first. There are various categories of models to consider. Firstly, you must decide between a foundation and a fine-tuned model. Foundation models serve as the base for more specialized versions. Typically, they are the result of extensive training on large server farms and demand substantial resources. Organizations like OpenAI, Microsoft, and Meta often undertake this initial training before making the models available to the broader community. These models are, for example, Meta's Llama 2, TII's Falcon, or Microsoft's Phi models. In contrast, fine-tuned models are more approachable. It involves taking a base model and further training it, using specific datasets to create a fine-tuned model. These datasets can be openly accessible and are often found on platforms like Hugging Face. Some of these models are, for example, Wizard LM, Mistral, or Vicuna. There is an important distinction between fine-tuned models, and this is whether they are designed for instructions or chat. Instruction models excel at tasks like retrieval augmented generation and summarizations. They are well suited for scenarios where providing precise instructions is essential. Chat models, on the other hand, are tailored for conversational applications, making them ideal for building interactive conversational agents. Let's take a look at model sizes next. The size of a model plays a crucial role in its capabilities and its resource requirements. Models come in a range of sizes, which is measured in the number of parameters. These sizes can vary from as low as hundreds of millions parameters to as high as 180 billion parameters. Typically, you will find models in the 7 billion to 70 billion parameters range. Compare that to likely the 175 billion parameters that GPT 3.5 has, or the rumored 220 billion parameters that each of GPT-4's 8 models has. The choice of model size should align with your specific constraints. Smaller models, such as 3 or 7 billion parameter models, offer fast inference times and can be more suitable for resource-constrained environments. But they lack understanding and precision in their output. Conversely, larger models like those with 60 billion or more parameters offer enhanced capabilities, but they might be significantly slower in generating responses. They also require a large amount of available VRAM, or video RAM. In my opinion, for most practical purposes, I would advise to consider models in the class of 30 billion parameters and up. For heavily resource-constrained environments, smaller models can be easily explored to understand their characteristics. They can be fine-tuned and honed into your specific use case. To fine-tune the data, we would need training data that is training data that is used to fine-tune a foundation model for knowledge in a specific topic, behaviors, or writing styles. These datasets can vary widely in their content or data harvesting approaches. Some datasets may focus on knowledge topics such as medicine or programming languages or literature. And some datasets are the result of novel ways to process and generate data. These approaches are often outlined in accompanying papers, and they're often worth a read. As an example, the Orca model was trained with data that was generated with the help of GPT-4. This process is explained in a paper from Microsoft Research. And since it's open source, others have used this approach to generate the publicly available open Orca dataset, which is used in many models today. There are continuous advancements in this field, and mostly with the goal to make smaller models as performant as large models that can be run on commonly found hardware. It is important to choose a model with training data that is aligned to your domain or application requirements to get the best results. Let's take a look what quantization is. Quantization is a technique that reduces the precision from the nodes in an LLM down from their usual 16-bit floats. The goal of this is to reduce the size of models and enable the hardware-constrained systems to run it. Ideally, a model fits completely into your GPU's VRAM. Typical quantization modes are between 8-bit and 2-bit. There are new model architectures, though, that are even going to use 1-bit modes. These are very experimental, though. Quantization is a lossy process, and you will mostly note this in 2-bit and 3-bit modes. But a 30 billion parameter model in a 2-bit mode is smaller and still outperforms an uncompressed 13 billion parameter model. You can see this in this graphic here. The lower you go, the better the model is, and to the right side you see the model size. The blue quadrant here that's marked is our 30 billion parameter model, which is better and smaller than the 13 billion parameter model in red. Let's take a quick look at file formats that are out there. Typically, you will find a gguf or GPTQ file format for your quantized models, and models that are not quantized come usually as a PyTorch bin file or a safe tensor file. And lastly, let's take a quick look at licensing. Models are usually governed by some form of license agreement. Some are released for commercial use and some aren't. There is a distinction between open access and open source. Some might be provided to the community as a pre-made model, and some might be even accessible through with all of their data, all of their weights. Now that you know about all of these distinctions in model types, sizes, training data sets, quantizations, you can make a well-informed decision when selecting the right language model for your use case. Let's take a quick look if there are already any questions. I see using open source models from Hugging Face. Are they safe to use locally? Yeah, they're generally safe to use. There's nothing that would execute on your machine like malicious code or anything like that. Model that you download from Hugging Face is basically the weights that the model is using to for using inference. So there's no code execution just in the model. Each model needs some form of software on your computer to be run, and there are different options there. We will take a look at one of those options today that plays nicely with the Llama Sharp package that we will take a look at today. So let's get to that. There are very few options for C# integrations at this time. The most accessible way, in my opinion, is to use the Llama Sharp package that I just mentioned. This Llama Sharp package provides bindings to the Llama CPP package, which is a C++ library that implements the transformer model. And for those that are unfamiliar with bindings, bindings are C# code that call into a C++ library and its methods from the C# code. In our case, it's the compiled shared library from the Llama CPP project. The results from these C++ calls are then returned to the caller for further use in C#. And that's how we can use these kinds of libraries in our applications. Llama CPP in turn supports many different language models. There are different types and these need to all be supported. And in my opinion, it is also delivers the best hardware support across platforms like macOS, Linux, and Windows. A big pro of this project is also that it's very active and it stays on the cutting edge in this space. So what are we going to do next? We will take a look at how you can install Llama Sharp in your project. Then we will take a look at an Instruct demo in the same vein. And we take a look at a comparison for a model called Wizard LM and its variants. We will take a look at different parameter variants and quantizations. After that, we will take a look at a chat demo. So how do we kickstart this installation process? So here we see our CS project file. And in our CS project file, we add our Llama Sharp package. Just imagine we already created a new project, for example, with .NET New Console. And you can either add the packages directly like I do here and demonstrate here, or add them via the package manager in Visual Studio or through the .NET interface on your CLI. There's on macOS, there's currently a problem in the current version where the delivered Llama Sharp or Llama CPP package is not correctly packaged. So we need to do a little workaround here and add the Llama Sharp project as a project reference instead of a package reference, and add the compiled output of our Llama Sharp package manually. So what does that mean? For Llama CPP, we need to compile it, for example, for macOS, and then and add it to our folder after we add the specific backend here. So for Mac, I use the Mac Metal backend, but for Windows and for Linux, you have backends for CUDA, for NVIDIA GPUs, or for purely CPU inference. For the workaround that I just mentioned, you will need to compile the Llama CPP project and add them in a library folder in your project, like I did here, and then copy them after you build your project. So let's dive into the sample code that illustrates an Instruct use case. First, I'll set the model path and initialize the model parameters with it. Then you can set these parameters to your specific needs. In my case, I set the context size to 2048, which is appropriate for my model's training parameters. I set a seed value to be able to reproduce my results, and I allocate 4 CPU threads for the CPU-bound inference operations. I then employ the memory lock that ensures that the application loads the entire model into memory during startup. Without this parameter, the model would load just before executing and unload after fulfilling a request. And lastly, and importantly, I specify the GPU layer count. Setting this to 0 utilizes the CPU exclusively. However, a GPU layer count greater than 0 progressively offloads more layers from the large language model into your GPU's VRAM. This distinction is especially relevant for NVIDIA GPUs. On macOS, on the other hand, this acts as a toggle, with 0 indicating off and 1 indicating on. This is due to Apple's Silicon's shared memory architecture, where all layers of the model are offloaded into your system memory right away. There are of course more parameters that you can configure, and you'll find these described in the API docs. Following these steps, we load the weights of the model into memory and create the context that is necessary to construct our Instruct executor. This Instruct executor instance is then used to perform the inference. Next, I load a text file with my Instruct prompt. This will serve as the foundation for the model's inference process and is basically what you add into your ChatGPT prompt window or similar. Next, we have a generator function that returns each token individually. This will give you that typical typewriter appearance when the inference runs. Here specifically, we use the Instruct infer async method. And this is in contrast to the chat demo that we will take a look later. We can also specify several inference parameters for each different run of an inference. So here we're looking at the temperature value, which is how random your output is, where 0 is adhering very much to the input that you give it, and 1 is more creative. We specify the max tokens to limit the output, and we use the anti-prompts string list to specify which token stops or which string stops the generation. So, of course, there are many more parameters that you can use, and these are all documented in the Llama Sharp and Llama CPP documentations. This is our prompt that we're using, and let's take a quick look at the format here, because every large language model that you use may have a different template. So Wizard LM uses a simple user and assistant template where before you start you have your system prompt, and then the user prompt comes after the user. The assistant token here is then the token that the large language model recognizes to start its own inference after. How does this look in practice? Let's run this example. You saw how the model was loaded, and then the generation starts right after. In our case, it is saying, "Hello YouTube audience, it's great to be speaking with all of you today for this Code Presents webinar on using large language models. I hope that you find my presentation informative and helpful in better understanding how to leverage these powerful tools in your own work." Before we continue with our comparison of the wizard LLM models, let's take a look at the chat and see if there are any more questions. All right, I see that Dean Wilds asks, brief what a parameter is. A parameter is it's a little bit complicated to explain in simple terms, but the parameters are the combination or the trained weights in your large language model that define what the output will be later on. They're usually floating points in this model that are saved in its layers. So it's very abstract and I think worthy of its own presentation, really. You can go really deep into that to understanding. There's a great presentation from Andrei, I get his name wrong every time, Andrei Kaspersky, sorry if I butcher that, where he explains and creates a transformer model from scratch. I would suggest you look that up online. It's something like writing GPT from scratch. In it, he goes through each of these layers and explains how they work. And this will enlighten you and what it means, what a parameter is. Earl asks, are any models more or less susceptible to hallucinations? Yes. Depending on its training data, depending on its size, a model might be more prone to hallucinations. Let's say, for example, we'll actually see a form of hallucination in our examples if we're going to take a look at in a minute. They might just come up with data that's not factual. So they hallucinate a piece of data out of the training data that it had, because it finds a connection between what you put in and the weights, the probabilities of your large language model. So that might happen. I would say the smaller it is, the more likely it might be. But you can prevent this with intelligent prompting, and there are ways that I have a link to a site that explains prompting techniques at the end of the presentation, and should be in the description below as well. You're often able to prevent hallucinations with proper prompting techniques. I see that Feng is asking that on the quantization chart that I showed earlier, a 65 billion parameter model at an 8-bit quantization is 50 gigabyte in size. Does this mean we can fine-tune this on a local computer? And can we use a CPU, or has it to be a GPU? It's a very good question. You will need, especially for big models, I would say 30 billion parameters and up, you will need a very powerful machine to do that. On both the RAM and graphics or video RAM side. I would not try to do this on common hardware. I would try to use online services like RunPod or other services where you can rent graphics cards like NVIDIA's A100 series or the H100 series, or multiple of those, to train these large models. Otherwise, it's not economical to build your own computer for these kinds of tasks. You'll end up paying upwards and north of $10,000 for this kind of hardware. How long would this take? It's hard to say. For one, it depends on the model size and the amount of training data that you use. If you're looking into fine-tuning your models on local hardware, I would recommend starting with small models like the 7 billion parameter models. And I will have a comment on those and their effectiveness in a moment. If you have a specific task that you want to train a model for, modern 7 billion parameter models are very capable already. So we'll take a look at this in our comparison now. So about Wizard LM. Wizard LM is an instruction fine-tuned Llama 2 model. It was trained using generated training data that was based on a technique called eval instruct, which trains data with very complex instructions rather than manual human input. And this eval instruct methodology rewrites initial instructions into more intricate ones using GPT-4 if I'm correct. So they take a simple instruction and then creates variants of that get more and more complex. Despite some of the shortcomings that it has compared to OpenAI's GPT 3.5, it showcases that there's a large potential of using AI-evolved instructions for improving large language models. The authors say that Wizard LM 30B, 30 billion parameters, achieves around 97.8% of ChatGPT's performance. There are leaderboards, there are kind of tests that are used these days to evaluate how strong a language model is, which has its downsides. These tests are starting to be kind of gamed a little bit, and they're to be taken with a grain of salt. But usually they have really good performance these days. I think this makes for an interesting choice though for instruction-based prompts. So I prepared a couple of examples for the following scenarios. The keyword extraction, sentiment analysis, then we'll take a look at text-based math problems, and retrieval augmented generation. Each of these tasks gets progressively harder and will show you where the strengths and the weaknesses of the model variants are. So, which model sizes are we looking at today? Again, we're using Wizard LM to have a model, the same model, but in different parameter sizes and different quantization modes. We will also use GPT 3.5 Turbo Instruct as a reference. I chose the 7 billion parameter 2-bit model for its very small size, I think about 2.9 gigabytes, and to give a good contrast to the large 30 billion parameter model with 2-bit quantization. Then we'll take a look at the 7 billion parameter model in 5-bit quantization, which gives us a good baseline to compare it to the 13 billion parameter model with the same quantization. And then lastly, the 30 billion parameter version should show us that the smallest 30 billion parameter quantization, it trumps higher quantizations of a model or of the model with fewer parameters. It also demonstrates the ability that you can run a medium-sized LLM, i.e. the 30 billion parameter, and I'm saying 30B for, it's kind of the class, can be 34 billion parameters, depends on the model, on something like my Apple M1 Pro with 32 gigs of RAM. All right, let's take a look at the first example. So here we have keyword extraction, and let me get a laser pointer here real quick. On the left-hand side, we have the prompt that I used. And for each of these examples, I used a few-shot approach. So I would give the LLM a example of what I expect, or one or two examples of what I expect, and then my actual question. And I want to know if it adheres to any formatting that I expect from it, like here, JSON format, and whether they get the question itself right. And I ranked the answers on a simple scale of either green, which is it adheres to the format that we expected and it got the answers correct. Then the yellow ones are a partially correct answer. In our case, for this one, it's if the output format is correct, the content might not be correct, or vice versa. The content might be correct and the output format might be a little bit off. And then you will see a red indicator for when the language model just couldn't create the correct answer at all. So going through this real quick, we expect it to grab keywords out of a question and then add them into an array of keywords that we could, for example, use for a retrieval augmented generation task. Notably here is that GPT 3.5, as well as all the others, have the format correct, but the 7 billion parameter models and the 13 billion parameter models get some details a little bit wrong. Like it says local LMA instead of LLM, I'm sorry. Which GPT 3.5 gets correct, and our 33 billion parameter model also gets correct. So this is a typical task that you might use a small model for. And in recent weeks, after I created these slides, a new model was released called Mistral. I don't really know what the correct pronunciation is here, which passes all of these tests without sweating. So there are continuous optimizations out there, and it's very important to keep a keen eye on the developments in this space. Let's take a look at the next task here, sentiment analysis. This might be an interesting case for when you have a lot of reviews or things that you want to analyze that someone sends you. I came up with an example about a comment for reviewing movies, and I want the language model to give me a feedback of what the sentiment is for each movie. In this case, I'm talking about Star Wars and Beetlejuice and Fast and the Furious, and it came up with the sentiments for these different movies here. And then I give it a random review from the internet and had the language models analyze this. As you can see here, GPT 3.5 is marked as yellow. And why did I do that? This is where GPT 3.5 actually hallucinated. As you can see here, while it gets the sentiment for the Serenity movie correctly and the date as well, and the sentiment and the date for the first Dungeons & Dragons movie from the 2000s, for the new Dungeons & Dragons movie, it came up with the date of, or release year of 2020, even though it was released in 2023. The sentiment across the board is correct though. The same thing with the 7 billion parameter models, where the model hallucinated that this movie was released in 2021. It's just incorrect. And the 13 billion parameter model did it a little bit better. It says unknown year instead. So I take that as it's a passable result, and we could parse this in our programming in some way. And the 33 billion parameter model as well, it gets it correct. It says new Dungeons & Dragons movie, and it just doesn't give us a release year because it doesn't know better, or it just doesn't know about a release year here. Across the board though, all of these models were able to correctly identify the sentiment. So if you have an application where a specific format is not necessary. All of these would be a viable option for you. And again, the Mistral model passed this test with flying colors, like the 13 billion parameter model and the 33 billion parameter model. The Mistral model is a 7 billion parameter model again. Now let's go to something harder, a text-based math problem. So here we ask a text-based math question that includes a base amount, and then we have different, we subtract and add values, but these operations are kind of masked in the text-based math problem. So the language model needs to identify which actions correlate to a subtraction and which ones correlate to an addition operation. I also ask it to go through each step individually to demonstrate its thinking process. So in our example, or in our question here, we say, I went to the market and bought 10 apples. I gave 2 apples to my neighbor and 2 to my handyman. I then went and bought 5 more apples and ate 1. There are some twists here for the large language model. Especially this sentence, I gave 2 apples to my neighbor and 2 to my handyman. It is not necessarily clear for a language model that the second part of this sentence, and 2 to my handyman, correlates with a subtractive operation, because it doesn't have the operative word gave in there. So that's the stumbling block there. It also needs to correctly identify that eating an apple is a subtraction. So let's see how they all did. I ran this test 10 times, by the way, to have an average of results. So GPT 3.5 passes with flying colors here. It breaks the steps down perfectly and reasons correctly here, and gives us the end result of 10 apples. The 7 billion parameter model with 2-bit quantization, on the other hand, gets several things wrong. For example, that first sentence that I specified here, it thinks it's 10 minus 2 apples instead of 10 minus 4 apples, because it can't infer that giving 2 apples to your handyman and 2 to your neighbor is both the same operation. It also thinks that eating an apple adds an apple to your bucket of apples, which I would really like personally. I would like to eat 1 apple and get more apples for that. The 7 billion parameter model with 5-bit quants had a 50-50 mix. So it was definitely better in this operation, but not consistent enough to consider this particular model for a task like this. The Mistral model, on the other hand, passed this test with flying colors again. It just demonstrates how important the training data and methodology behind it is. And the 13 billion parameter model and 33 billion parameter model both had no problems answering this question throughout all of the 10 test runs that I did. Next, retrieval augmented generation. This is really, really tough. So my idea was to set up a scenario where I have a fictional electronics shop online, and a user ordered a product that became unavailable because it was out of stock. Then I gave the LLM an alternative product with both the specifications and prices of the original and the alternative product. I asked it to write an apologetic letter that the original product wasn't available anymore, and to offer a 10% discount to the user for the inconvenience if they want to order the alternative product. The GPT 3.5 Turbo model correctly identified both the prices of the original product with $149 and of the alternative product here with $188, and was able to correctly calculate the discounted price of $169.20. It also asserted that the price of the alternative product is slightly higher than that of the original product. I also need to mention that the product descriptions are kind of vague and don't have a great data quality. So there's an additional hardship there for the large language model to identify which pieces of information, for example, come up multiple times. Like the product name is written incorrectly for one of these products once, but multiple times differently. So you would have to figure out, the product name is incorrect one time, but it says it a couple of times correctly. So should use the one that was mentioned more times than the one that was incorrectly stated. The 7 billion parameter model had no chance here. The 2-bit quant variation here. It got the model name wrong. This was one of the issues that what I'm referring to just now. It would be trick key G4 instead of G2. And it also incorrectly or did not correctly identify the prices here. And from its calculation here, 198 and 188, I assume that instead of a 10% discount, it applied a $10 discount here. So no good result here. The 7 billion parameter Mistral model, again, also did not get this one correct. So this is kind of where things break down, or start to break down with these smaller models. The 5-bit quant similarly has similar errors here, although it correctly figures out which model name is correct here, G4, and it finds the correct price. It's partially correct here. It has some interesting style here, writing to inform you that we regret to inform you. And I gave that a thumbs down because it sounds kind of odd. And to highlight this for in a moment, the 13 billion parameter model got everything correct though. It omitted some things, but it found the correct price and it was able to apply the discount correctly, which surprised me, to be honest. The 33 billion parameter model had a couple of mistakes. It also did this stylistic choice here, which is odd, writing to inform you that we regret to inform you. And it made a more severe error by saying that the alternative price is slightly lower than the original price, which is just not correct. We might be able to counter these kinds of things with better prompting and maybe different temperature settings, maybe different inference parameter settings that we took a look at earlier. So definitely something that you would have to try out for yourself. So overall, for many of these tasks, especially with the Mistral model that I mentioned, a lot of these models hold their own against GPT 3.5, which I found surprising that a 7 billion parameter model was this good at some tasks compared to GPT 3.5. But overall, if I was going to do something production ready, I would probably choose something in the 30 billion parameter class and upwards, because the consistency of answers is just better. And more complex tasks like these can't be solved by smaller models. If I have some smaller tasks though that need to run for efficient purposes, for things that are maybe the first step to process some data before you give it to a larger model or to a paid service like OpenAI's, and especially GPT-4, which is quite expensive. These kind of small models might be a really good option if you're looking for different steps of processing with language models. Let's take a quick break and look again at if there are any questions from the chat. So there's a, okay, how do you fix this prompt with prompt engineering? Would you add an extra instruction to not include year or uncertain? Yes, you could, for example, structure the list of, and maybe we can just go back real quick here. You could structure this list of outputs here with a variation where the year is unknown, and say unknown, and then also instruct it in the system prompt to type unknown or something that you can expect and easily filter out in post-processing. So it's a combination of your system prompt and the output example that you give. Then there is the, running it locally. I have it on, I have it in my video, like I showed earlier. I will show another example with the chat, with a chat instruction or a back and forth. Running it live though, I don't want you all to wait for my machine to work through all of this. Small things work really fast, like the first example that I gave ran in 6 seconds. My later demonstration, the context grows quite a bit and you have a little bit more of a delay. I don't want to put you through all of that. So hosting a model locally, there are different options for that that we can use. And one of it is the Uba Buga interface, or it's or Llama CPP could be used just by itself as well if you want something like an API that adheres to OpenAI's API specifications. These kinds of things exist, but then we're talking about running them on a server and accessing it through an API instead of baking it into your application specifically. When choosing a model, is there something that you look for in a description, or do you take a chance and run these tests? Usually both. There's the descriptions of a model on Hugging Face gives you a good idea of what this model is useful for. For certain tasks, you will find specific models. There are models that are stronger in math applications. Other models are stronger for coding applications. Yet again, others are good for chat applications where it's more conversational or a creative output. So it kind of depends on that. And then you run some tests if the model performs as you expect it to. The other place where I always look, and it's a link in the description and at the end of the presentation, is the local Llama subreddit on Reddit. The community is very active, and there are a lot of people who run more comprehensive tests and publish them, so you can get a good feel of which models and variation and fine-tuned models might be right for your use case. And then there's a question, can you comment on Bloomberg GPT, 60 billion parameters, 700 billion token training data set? I'm not familiar with Bloomberg GPT. I think that's a closed source model. I've heard of it, but I'm not quite familiar with that, to be quite honest. So just in retrospect here, comparing this, tiny models or small models like the 7 billion parameter models are useful for simple tasks where inaccuracies might be tolerable, and small models like the 13 billion parameter model are getting progressively better, with medium-sized models and up being more eloquent and being able to pay more attention to details in your prompt. Again, this was from a couple of weeks ago, and the Mistral model with 7 billion parameters has shown me that even small models become better and better. This just goes to show that the community that there is a great potential through the community efforts and new training techniques to improve these models, especially for for specific tasks. So let's take a quick look at that chat demo that I mentioned earlier. So here we again set up our paths and our parameters, this time with a context size of 4096. We again create our contexts with our weights in the same way, but then we use the interactive executor here for an interactive to create a chat session with it. This session helps you to roll back to a state that you can save. There are for that, look into the API documentation. With the history and the save state, you can recreate the conditions at an exact point in time. Here we're setting up the different tokens for our template, which will be a little bit different from the one that I showed you earlier. Then I load the prompt for the chat. It's kind of the priming prompt that I use to get things rolling. Some fancy output for our console to have a good distinction between what we type in and what is generated. And to pick up on a quit token, we define that as an end of conversation prompt. And here in our while loop, we just continuously looking for new user input until the user says quit. Then we again have some output here that you will see in a moment. And our generator function that uses the chat async method here from our session compared to the infer async from our Instruct executor earlier. And then our inference params that where I use the temperature of 1, which for chat applications is more appropriate because we want more creativity, more differing conversation or answers. And we set our max tokens to our context size to have a conversation that just goes on, and wait for our anti-prompt, that is LLM for the large language model to stop generating when it encounters this. Then we have our output for the tokens and some output afterwards, and then we go back into waiting for user input. If the user says quit, then we'll quit and just print a goodbye message. And this is what it looks like. This is our prompt first with our different tokens or templates that the large language model was trained on to recognize and to act upon. So our system message being our code AI LLM or assistant. Then we prime our conversation with a little back and forth. And at the end, we give it a negative prompt here because I don't want the code AI to talk about anything else but code and technology and programming specifically. So we're saying, hey, what is an antelope? Sorry, I don't know what an antelope is. Just as a demonstration for a naive way to kind of tell your large language model to not answer certain questions, which is what services like OpenAI do in a naive way to prevent things like unsuitable content being generated. And this is what that looks like in practice. So in VS Code, I run my program and you see our priming prompt. And I ask it, how can I get started with programming in C#? And this is the 7 billion parameter Mistral model in this case. It gives a really good starting point for people to familiarize themselves with C#. Then in contrast, I ask, how about Java? It looks at the context and recognizes, hey, I want an instruction on how to get started with Java now. And saying, what are important differences between these languages? Now it figures out I previously spoke about C# and Java. Now it takes that information to generate a comparison between the two, and a pretty expansive one for that. As you can see, it goes on for a little while. And feel free to revisit the video to look at the output in more yeah. So, and then at the end we're looking at summarizing the conversation, which it does just flawlessly, just to demonstrate that these smaller models are capable of doing a good job at summarizing content like this. So that brings us to the future of large language models. So what does the future hold for large language models? On the one hand, I'm thinking that we will achieve even better performance through improved training data. And I was proven right after writing these slides by the Mistral model that I've been mentioning a couple of times now, where improvements in the training data has been leading to improvements in the model output for smaller models. And this is also what I expect continuing, where the continuing development goes, that smaller models get trained on data for specific tasks, while your large models get trained differently to be more all-around capable. I also think that there's going to be changes in the actual architecture of models that might replace something like the transformer model. The transformer model was a huge milestone, of course, and is what all of our language models today are based on, but it also has a couple of drawbacks, like the huge resource requirements for training and inferencing. There are certain models on the horizon, like the retentive network model from Microsoft Research and the team at Tsinghua University that they demonstrated in a paper in July of 2023, which I linked in the description as well. And you can see that the GPU memory usage is significantly reduced here to about 3.4 times that of, 3.4 times reduced compared to other transformer models. The throughput for inferencing is increased, and the latency as well as decreased. And the scaling curve for the model sizes, the perplexity value is significantly improved as well. Now, another thing that I see coming, or where we will see more developments, is multimodal models, like what was recently released by, I think, OpenAI GPT-5, so to say, where it can take an image and analyze that, and then describe the image using the language model. There's also developments in creating longer context lengths from up to 128 tokens, and I've read like there might be even developments to be able to use as many tokens as you like. And then there's a kind of a doomed scenario called model collapse, where it was demonstrated that when you train models on the output of other models, over time the output will become inconsistent to unusable. And this is because if you train a model on another model and then train it, it's kind of like overwriting an old cassette tape over and over again. We're only choosing the most likely tokens at each time. And if you do that over and over again, more uncommon scenarios, more uncommon tokens will be forgotten by the model. And your output will become pigeonholed to just the just the tokens that are the most likely. So eventually, you'll just get garbage, basically. All right, that was a lot. What have we talked about today? So we discussed why you would want to run a language model locally. We discussed the aspects of control, privacy and compliance, and offline access. We talked about the different things that you would want to take a look at when you choose a model, like model types, model sizes, training data, quantizations, file formats, and maybe licenses. And we looked at how you can use Llama Shark to integrate your language model that you chose into your C# application. And we took a look at the different wizard LM variants and how the different parameters and quantization modes influence the results. And we took a look at what the future of open source language models holds. So let's get to just a few announcements. Oh, sorry, the resources first. Let me get myself out of the way here. As I said, Llama Sharp and Llama CPP are the projects that we use on, and you can find these on GitHub here. Then I strongly recommend you, as does Andrej Karpathy, and see, that's his name. Sorry that I misspoke earlier. For even he is looking at local llama for his source of information, and I think that should tell you a lot. You can find quantized models on Hugging Face. There's a user called The Bloke, and check him out. He is a stellar guy who provides the community with quantized versions of newly released models pretty much a couple hours after they are released. He's on top of that, and everyone is very, very grateful to him for doing this service for everyone. Then you have Uba Booga, which is a web UI that you can use with a inference servers in the background. Or if you want to have something that's more bundled into an application, you can take a look at LLM Studio, which is a very well made application for trying out language models. And as I mentioned, at Prompting Guide AI, you will find really good tips at how you can create your own prompts and how you can get better at that. Links to all of the papers that I mentioned should be in the description below. And with that, let's just get to some announcements from the start. Again, if you're interested in using our AI consulting services, please visit codemag.com/AI. And if you're interested in our executive briefing, please visit codemag.com/executive briefing. Then please also look at our code staffing arm at codestaffing.com. And if you're interested in working with us, go to codestaffing.com/careers. Tune in for our State of .NET on the .NET 8 release on November 15th with Marcus Egger. You'll find this at codemag.com/stateof.net, where you can register for this event. And we have upcoming code training classes where you can learn on how to develop your own applications with the OpenAI and Azure OpenAI ChatGPT APIs, and how you can build your own co-pilots for your own apps with these services. And if you're interested in it, these training classes can be individualized and held as private classes and mentoring sessions for you or your organization. If you're interested in that, go to codemag.com/training. Also, don't forget to subscribe and ring that bell to never miss any of our content here on youtube.com/codemag. And if you're interested in the slide decks and recordings, go to the websites for our State of .NET or the Code Presents on the respective subpages of our codemag.com website. If you're interested in winning a $100 Amazon gift card, please take part in our survey that will help us get better at our Code Presents and figure out what you would like to hear about next. And let's take a last look quickly at the chat and see if there are any more questions. So Brett is asking, is there ever a concern about variance among so many different models? I'm not quite sure about that question. Concern? I don't think so. The open source community is just very active in trying to figure out what works and what doesn't. And it just tries to generate models for all kinds of use cases. If you look at what training data is used and what training scenarios are used, I wouldn't say concern. I think the community tries to just have something that works for you specifically or for everyone, and it's just a lot of experimentation. It's the very early days. ChatGPT came on the market about a year ago now. we're in the crazy days, so to say, where things are being tested and tried out, and I think soon we will land more and more on more like we'll probably see something that narrows down in methodologies and how to generate training data effectively and get models better and better in that way. Tunak Weil is asking, are these models capable of solving categories of problems such as proposing the correct booking and accounting of an invoice based on its content? I can imagine that this kind of problem can be solved with a larger language model, especially if you have training data and you are able to train or fine-tune a model based on your data. You could give it, let's say you have a invoice that has a specific format and you expect it to extract a piece of information that has specific context around it, then you'll probably be able to train a model to adhere to the format that you give it and give a consistent output in its generated answers there. So if there's no more other questions, thank you all for attending today's Code Presents. I'm really grateful that you all attended and stuck with me. This was a very dense presentation. And I hope you're able to use this information to create an interesting application. If you're interested, again, let's go back to the presentation here. You can ask questions, send us a message here at info@codemac.com or at my personal email, pbauer@codemac.com. I'd also just love to hear if you come up with a cool implementation idea and you just want to show me. I would love that. So feel free to contact me with your questions. I'll try to get back to you as soon as possible. And yeah, let's get to talk there. Thank you all so much. I hope that you'll join us again in the future for our Code Present series. And until then, have a great day, have a great evening wherever you are, and see you next time. Thank you.